Before I start, I just wanted to acknowledge a few people in the audience who have had very good discussions with me on this work and who've been supportive. So I want to acknowledge Doa and Ryan Dewey, Luisa Capanolo, Gonzalo, and Abby for their support and for their persistence in being okay with listening to me infinitely. All right. I want to also frame what I'm going to talk about right now. So this is about a phenomena that people think happens in the Earth's magnetosphere ionosphere system due to solar wind driving. And what I want to sort of demonstrate is that that interpretation of that phenomena is heavily influenced by uncertainties in our solar wind measurements. And these uncertainties are not trivial, so I'd like to persuade you guys about that. All right, so heliophysicists, like in general, like many other scientists who study these natural systems, employ, this technique that we would generally call regression analysis. And we do this regression analysis to infer how a system responds to external forcing. For example, a major question in heliophysics is how the Earth's magnetosphere ionosphere system responds to forcing from the solar wind. And fundamentally, this regression analysis is a method to analyze how two or more parameters are associated with each other. So the most familiar form of this technique is linear regression, where we assume a linear relationship between the parameters of interest. So the thing is, many modern machine learning techniques that we use are basically a nonlinear, non-parametric regression analysis. So one of the major results you get in the magnetosphere ionosphere systems studies using nonlinear regression analysis is that between solar wind forcing and the ionosphere response, there's this apparent observation that no matter how strong the solar wind is, there might be an upper limit to how much energy reaches the Earth's ionosphere. This phenomenon is known as the polar cap potential saturation. So I'm going to explain to you briefly what polar cap potential saturation means. So solar wind electric field drives day-side magnetic field reconnection, and its effects are transmitted through equipotential magnetic field lines to produce convection in the polar cap ionosphere, just the kind of thing that Doa was showing examples of the previous talk. And that convection corresponds to a cross polar cap potential, dawn to dusk. And data seems to suggest that this polar cap potential increases linearly for low values of the solar wind strengths, but it tends to saturate at high values. So over the past 4 decades, there are several theories that have been proposed to explain this saturation, but there has been no clear consensus on any single theory. And in this talk, I want to focus our attention away from any of these models that try to explain this data, but explore whether our interpretation of the data is valid. So if you go back and look to the actual measurements that these models are attempting to explain, the vertical axis here represents a proxy for the polar cap potential, namely the polar cap index, which is essentially the maximum amplitude variations observed from magnetometers within the polar cap. The horizontal axis is the solar wind Canley electric field at L1, which can be thought of as the upper limit of the magnetic reconnection rate in the day side. It's measured using the wind spacecrafts at L1, propagated to the bow shock using propagation models from the Omni database. The cyan line is the line of equality between the two axes. Note that both these measurements or like parameters have the same units. And the green line is the nonlinear regression function, in this case, a simple conditional expectation of the polar cap potential given the measured solar wind electric field spanning 20 years of the database. So my goal in this talk is not to question the accuracy of these theories that I just mentioned before, but instead I'm questioning whether this nonlinear regression function that we infer from the data is a reflection of reality or not. Can we actually trust this regression analysis? So to answer that question, we must first recognize that the solar wind data has some important sources of uncertainty. And when we talk about uncertainty in measuring solar wind data, we usually think of like an instrumental error. However, most of the error comes from the assumptions we make rather than what these instruments report. So when we measure solar wind parameters, we mostly do so at 230 Earth radii upstream of the reconnection region. And this is the L1 libration point. And hence, we do not have access to the solar wind electric field that drives magnetic reconnection much closer, that is at the dayside magnetopause. So hence, we have to assume a propagation model of the solar wind, like Doa was mentioning previously. And this assumption results in a random error in the times at which the solar wind, we think the solar wind reaches, say, the bow shock. Furthermore, it takes time for reconnection electric field effects to propagate down to the ionosphere. And space physicists usually assume a constant time interval for this propagation, like again, Doa mentioned. And this will lead to additional uncertainty in the solar wind electric field values associated with the polar cap potential that creates this, the solar wind electric field creates. So thirdly, there is another issue. We assume that the solar wind parameters do not undergo any change between L1 and the magnetic reconnection point at the day side. And this is not true. There is a bow shock and a magnetosheath consisting of plasma between the L1 and the reconnection site. And within this region, the clock angle of the interplanetary magnetic field, which is extremely important for the reconnection electric field strengths, can undergo random changes, thereby creating a random uncertainty in the magnitude of the solar wind reconnection electric field. There are many more assumptions that we space physicists make, such as reconnection happens mostly at the nose of the magnetopause, or that the magnetopause remains stationary, or has a symmetric structure, or that the solar wind is uniform. And none of these are true, right? The real scenario is much more three-dimensional and variable. So these at least create random errors in the solar wind measurements. So here's the question, right? What happens when there is uncertainty in the input to your regression analysis? To answer that, I think we should go back to the origin of the term regression. So in the late 19th century, Sir Francis Galton, Charles Darwin's half-cousin, who's responsible for coining words like correlation and percentiles, observed that extreme characteristics in parents do not seem to be passed on completely to their offspring. In this particular example, he found that on average, children of tall parents seem to have a shorter height than their parents. Likewise, on average, children of short parents seem to be taller on average than their parents. And this phenomena he named regression to the mean. You will find this also as like regression dilution, or linear regression bias. And I think this bias is a consequence of the fact that the height of a parent is an erroneous estimate of the genetically inherited height of a child. There are environmental influences that cause a normally distributed random uncertainty in a binomially distributed process of height inheritance. So it's important to note that this bias is not a causal phenomena, it's a statistical effect. And Galton tried to quantify this statistical effect. And in the process, he invented linear regression analysis and coined the term regression. And this was the original meaning of the term regression, that extremes tend to regress towards the mean of the distribution. And I've always thought it pretty curious as to why we call fitting certain functions on data regression. I mean, regression simply is the opposite of the word progress, right? Or progression. And where is the connection? Basically, the thing is that we have forgotten that connection. And the word regression has taken a life of its own. And it's useful for us to remember that hidden in the historical meaning of the word is this important concept of regression to the mean. So coming back to the polar cap potential saturation problem, what this means is that there will be a bias in the regression function due to random uncertainties in the solar wind forcing or input to your input parameter to your regression. And it will be biased towards the mean of the input random variable. The nature of this bias is in the regression function depends on the probability distribution of the input random variable and the nature of the uncertainty. Because the distribution of drivers has many more points at low values than high, errors in the driver will lead to a mistaken association of a response to a high value of driver with that of a low value driver. And as the solar wind electric field is log normally distributed and the uncertainties can increase with the magnitude of the driver, the regression to the mean becomes more acute the greater the solar wind electric field. And hence your regression function will appear to have a non-linearly increasing bias or even appear to saturate. Now, if this is unclear, don't worry. I'm going to explain the same phenomena in another context. And in the context of measuring a time series signal. So in general, any signal is a stochastic process with an underlying probability distribution and an autocorrelation function. And it is mostly the case that high and extreme values of the signal are rare compared to the average value, which is more common and lower. So, and in signals that are propagating from a point A, where you make a measurement, like the solar wind at L1, but you're interested in its value at a point B closer to you, like in the day-side reconnection region, you might have some serious random errors in the timestamps you assign to the signal. In this particular instance, let's say the timestamps are off by about 10 minutes. Hence, the measured value at a time instance, like this is the black line here, is different from its true value shown in blue. And in real life, you only have access to your measurements, the black line, and not the true signal, blue line. Now you say that you are interested in measuring the peak value of a signal, which in this case is 3.1 millivolt per meter, and its corresponding true value happens to be 2.2 millivolt per meter. And this won't be the case all the time, since the true value given your measurement depends on the time uncertainty you have. So the question we should ask is, what is the statistically expected true value given a measurement? We can find this out by doing a Monte Carlo simulation with each iteration being a different hypothetical instance of measurement time errors. And what you see on the right is the conditional probability distribution of the true value given an erroneous measurement of 3.1 millivolt per meter. So what you see is that the expected true value is much closer to the mean of the signal than your specific measurement. And this statistical phenomena is related to the regression to mean that Galton uncovered in the 19th century. And here is the main point. If you were to try and find the polar cap potential response to 3.1 millivolt solar wind electric field, you are in fact observing the polar cap potential response to 1.6 millivolt per meter. No wonder the polar cap potential appears to not live up to the electric field that is driving the reconnection, especially during extreme solar wind strengths. That is, when you think the polar cap potential response you see is due to a particular solar wind electric field, that is not true. It's actually, on average, caused by a field value that is lower and closer to the mean. Here's another way to illustrate how uncertainty in the time of measurements leads to the nonlinear regression function. Here, the x variable is the true value and w is the erroneous measurement. The error here is in the measurement timestamps. You can think of as a propagation delay error of any signal. Now, if you plot the conditional expectation of the true value given the erroneous measurement for 0 error, you will see that the line, there'll be a line that is, the line of equality, the 45-degree line here, black dashed. Now, if you increase the time uncertainty, which is shown here in percentages of the autocorrelation time constant, you see that the line starts bending non-linearly towards the mean of the true value. Now, you can analytically derive this completely from first principles, and you can look at it in more detail in this manuscript that I've uploaded in archive. So to precisely estimate how uncertainties affect the polar cap potential response that people see in data, we constructed a simple error model, which says that the uncertain solar wind electric field estimate is equal to the true solar wind electric field with an uncertainty in the time of measurement, basically comes from the lack of a perfect propagation model, and uncertainty in the magnitude of the measurement comes from many processes that happen between L1 and the ionosphere, but a major one is the IMF clock angle can undergo random changes as it crosses the bow shock. Now, the uncertainties we assume here are unbiased, that is, they are zero mean and random, and we base them on these previous literature. Finally, we assume that the true solar wind parameters have stochastic properties that we observe in the data, that is, they are log normally distributed, and it has an autocorrelation function with a particular time constant that match with the data. Now, here's the result of our analysis. In this plot, the green line is the regression function from 20 years of data. You've seen this before. And here's the surprising thing. The regression function estimated by the Monte Carlo model, which is the purple line, seems to match surprisingly well with the nonlinear regression function inferred from measurements, which is the green line. What this suggests is that random error in the solar wind electric field estimates might be sufficient to explain this nonlinear response of the polar cap potential that we see in data when we infer the data without correcting for the uncertainties. And we should note that uncertainties will always be there in both the input and output parameters of a regression. And hence, there will always be a bias in the regression function. So the extent of nature of that bias is the only question we have. Hence, we must correct for these uncertainties before we interpret anything about the association between parameters on which we perform the regression analysis. For linear regression analysis, there are methods like the orthogonal regression to correct for such biases. However, for nonlinear regression, we cannot use those same techniques. One of the simplest techniques we can use is called regression calibration. So if you have access to the expected true value of an erroneous measurement, we can simply transform each erroneous measurement to its expected true value. This, of course, is a mere statistical correction, but it will provide us with an unbiased regression function. And in our case, we have access to the expected true value given the erroneous measurement using the Monte Carlo solution of the error model that I mentioned. So what does the regression calibration actually do? It simply shrinks the input axis non-linearly based on the assumed uncertainties. So when we do the statistical correction to the actual data, that is the solar wind electric field estimates from an L1 monitor and we associated that with the polar cap index measured on the ground in the polar cap, we see the regression function is actually linear. So this could imply that when correct for the solar wind propagation uncertainty, polar cap potential is actually varying linearly with solar wind forcing. That is, the upper limit of the energy transfer from solar wind to ionosphere could merely be a perception due to uncertainties in the input variable, leading to a nonlinear bias in the regression function. This is a significant result if it's true, because what this means is that the response of the magnetosphere-ionosphere system can be much higher than what the saturation of the polar cap potential suggests. So here's the thing. We've been asking our models to explain an incorrect inference from the observations. However, before we ask models to explain the data, we need to be quantifying the uncertainties in the SolarWind drivers better. We need to be cognizant that many of these uncertainties come from assumptions that we are making. And it is not sufficient to simply put a number to the uncertainty. It is important to know the probability distribution of the uncertainty and how the uncertainty varies with the magnitude of the SolarWind driving. Once we have all this, then we need to correct for uncertainties and uncover the correct average response of the ionosphere to SolarWind driving. Now, it might be linear, like what I've shown, or it might be slightly nonlinear. It depends on the uncertainties we actually have. Whatever it is, that is the response which we ought to be asking the theories and models to explain. So, what does this all mean? Uncertainty in measurement of the input to any nonlinear regression analysis can lead to a nonlinear bias in the regression function depending on the stochastic properties of the input. When we apply this insight to the polar cap potential saturation problem, we find that the effect might just be a perception caused by uncertainties in the SolarWind forcing. Reducing the uncertainty will indeed reduce the saturation effect. However, we do not necessarily need to reduce the uncertainty. We can quantify the uncertainty and then correct for it. Correcting for the uncertainty reveals that the ionosphere response to SolarWind forcing might actually be linear. Hence, it's possible that no new physics needs to be invoked to explain the saturation effect, because the saturation effect may just be a perception. So many of us here in the seminar who plan to use machine learning, or you're using it, are probably interested in how such a bias due to random errors can affect machine learning-based studies. So if you use machine learning to make predictions, nonlinear regressions to make predictions, as long as you continue to use the erroneous input you develop the training data set on, my speculation is it shouldn't affect your predictions too much. Correcting for this uncertainty statistically may improve prediction accuracy, but this is something we ought to explore. The prediction is not the only utility of machine learning and other regression-based models. One could use them to provide a bridge between, say, two physics-based models, or simply as an input to one physics-based models. For example, when we use, say, Sivadas magnetic field models that is developed, for the Earth's magnetic field, it's developed partly based on measurements from the SolarWind monitors as input to some physics-based model. This nonlinear bias might affect the outputs of the physics-based model unless we correct the SolarWind input that the Sivadas model is based on. There are MI coupling models that use polar cap potential saturation as a given in their construction. So if the saturation is merely a result of uncertainty, this will lead to erroneous conclusions from the MI coupling models. So I'm sorry, I think definitely went over time, but this work is undergoing peer review in a journal, and the preprint is uploaded in an archive. And I would love to take a few questions and discuss the time we have left.